you very much, everybody, for coming. So I'm going to make a very brief presentation. It's a great pleasure to introduce Professor Juan García-Bellido. Juan is an internationally recognized cosmologist. He has a very extended career. He's worked in many different subjects. He's an expert in early universe cosmology. He has made very important contributions for the topic of inflation, primordial black holes, CMB, and gravitational waves, and many others that he would be able to tell you more than me. He's worked in international centers like CERN, Imperial College, Stanford, and now he's in Madrid, in the IFT in Madrid. And we are very happy to have him here today to talk about gravitational waves. This is his first talk, I believe, after a very prestigious award that he just got last week, which is the Blas Cabrera National Research Award. And we are very proud of having him with us today. Okay, the floor is yours.
Thank you very much. Thank you very much for the invitation, Jose Juan. It's a pleasure. Actually, I was here 10 years ago, 2016, in an extended visit. And it's always a pleasure to come back to the Universidad del País Vasco. So this university has always been an interesting center for cosmology, an attraction for people that were always making new contributions and thinking seriously about observations and the connection between theory, early universe theory, and observations. And it has been attracting through the Ikerbasque a series of very bright people, among others, some of you are here in the audience. And I think it's a pleasure to see how this center has become a lighthouse for other centers to take as an example of how things should be done in this area. So I'm very happy to be back here. It's very encouraging to see the growth of interest, and clearly seeing all of you here, trying to understand things, new things that have opened up in the last 10 years since I was here. So in the last 10 years, we have matured as a community in the context of gravitational waves. In 2015, there was the first detection of a gravitational wave event, September 14th. And this has opened up a new window, and not only for understanding of astrophysics, which indeed it has, but also for the understanding of the universe, the origin of the universe, as well as the way we map our location in the universe. Okay? This will allow us to measure distances to objects, will allow us to determine the rate of expansion of the universe today, will allow us to know what is the content, matter, and energy content of the universe. But we're only scratching the surface at the moment. We only have about 300 events or so, as I will describe in this very general colloquium on gravitational waves. But in order to reach that level, let me very briefly introduce the whole subject. Obviously, we need general relativity to describe this, and who other than Einstein to show here, because without somebody like him, we would not have even the lightest clue what was out there, much beyond the solar system. And it's thanks to him that we understand that gravity is no longer a force. It's actually nothing but the curvature of space-time. Space-time, the location where things happened, okay? Where the rest of the physics, like electromagnetism, ordinary nuclear forces, etc., happen in some location in space and time. He realized that this notion was actually a full one, space-time, and not only that, that space-time was dynamical. It reacted to the presence of matter, okay? So John Wheeler put out something which encapsulates very nicely the idea of general relativity, and that is that matter tells space how to curve. Space-time is no longer flat and Euclidean, as we thought until then, but space also tells matter how to move. And this duality, this nonlinear behavior of gravity is absolutely essential. Without it, gravitational waves would not exist, okay? So clearly, we have to understand how this happens, and there are some tools that general relativity puts forward based on differential geometry, Riemannian geometry, etc., which describes the way objects move in this space-time and how space-time is curved due to the presence of matter. This is a very simple realization of the moon moving around the Earth, where you see that both the moon very slightly, but certainly the Earth, is curving space. Obviously, we're projecting out from 3 to 2 dimensions in order to visualize it. This is space-time is shown here like a flat rubber sheet, but actually space-time is 3-dimensional, and we know that indeed space is curved due to the presence of matter. And notice that the difference with respect to Newton is that there is no force that maintains the attraction between the moon and the Earth. What happens is that the moon is moving in curved space in free fall. There's no force on it. It just simply, its free motion in space is dictated by the curvature of space. Light curve moving in this curved space-time might turn around and make a close orbit like that of the moon. Any object, not just the moon, would move along those what are called geodesics. Now, of course, if a space-time reacts to matter, that means it's dynamical. If you have some distribution of mass which moves in space, it will curve space along its motion. Okay? So as it moves, as you could see in the case of the moon, in its orbit around the Earth, it's perturbing space around the Earth also. If the object is rotating, it is also perturbing space. It induces what is called the precession, spin precession, or if you want, frame dragging, so that some aspect, due to this spinning object, will induce a change of motion of an object in this space-time. Okay? Now, of course, it's dynamical, so it curves wherever there's matter and energy in the universe. So you might ask, how can we see this? How can we, for sure, convince ourselves that this curvature is inducing changes in the trajectories of particles? Among others, the easiest things to observe at high distances are photons. Nowadays, gravitational waves, but otherwise, photons. They don't have any mass, they have energy, and they curve. Their trajectories are no longer straight lines in space-time if there is matter. For instance, if this matter is made out of a big cluster of galaxies, like here, where you can see a few galaxies orbiting around the central object in the cluster, you see that light that travels from this galaxy, which does not belong to the cluster, is way behind. The trajectory of light will be bent by the presence of this cluster and will curve around space, and eventually, if the matter within the cluster is sufficiently large, the strength of the bending might converge light on us, which are observers on Earth. Okay? So it's possible that we might see more than one trajectory, more than one light path. That means that projected out, we would see 2 images, or 3, or 4, or 5. Those different images will tell you about the presence of matter between you and the object, which has curved the space, and you can use this to measure or weight the amount of matter which was between you and the object. Okay? So that's a very crucial aspect of general relativity, a prediction, the bending of light, which was already in his first papers of Einstein, which later he developed, understood as the lensing of light, microlensing and strong lensing, even now weak lensing, small distortions in the objects behind the distribution of matter that large galaxy catalogs are already observing and using in order to determine not the distribution of the masses of clusters, but the total mass in the universe, okay? Omega matter. So indeed, we are using the fact that matter is curved space. But why didn't we notice this before? Why did we have to wait until the 20th century, the beginning of the 20th century, to realize that space-time was curved? That's because the effect is really tiny, okay? So if we write things in terms of a fundamental quantity, a dimensionless fundamental quantity, which is related to the deviation from perfect flatness of your space-time, both in the zero-zero component of the metric, the time component of the metric, or in the spatial component of the metric, that quantity, the Newtonian potential in c squared units, gm over c squared r, it's a dimensionless quantity. Gm over c squared is one distance, typically relates 2 times this is the Schwarzschild radius, and the size of the object is characterized by r. Now, for the Earth, that quantity is 10 to the minus 10. Well, that's not much. Of course, in the time of Newton and even in the 19th century, we never had resolutions that would go back to 1 part in 10 to the 10. No way. We could not resolve the fact that space-time was not flat to 1 part in 10 to the 10. Of course, we need objects which are much denser. For instance, things like Jupiter, whose size is much bigger than the Earth, and its mass is so much bigger, that this quantity begins to grow, 10 to the minus 8 for Jupiter, 10 to the minus 6 for the Sun. Okay, here we have 1 in a million, just about to be resolved. For instance, looking at the light from distant stars as they travel near the Sun in an eclipse. Similar, a solar total eclipse, similar to the one we're going to see in a few months, okay, in the 12th of August, for those in the north. You may want to try this experiment yourself if you have a telescope. Actually, it's not so difficult. I encourage you to do it. Because at 1 part in 10 to the 6 is sufficiently big, although it's small, that you might see the variation in the location of the stars outside because of the bending of light by the Sun. Okay? Now, of course, if we go to larger objects, still stars, but in this case, neutron stars, those are objects which are way more compact, much more dense than the Sun. They are the aftermath of the remnants of big explosions in the universe called supernovae, which leave behind remnants which could be either a neutron star or a black hole. In the case of the neutron star, there is a maximum mass that it can have to maintain through the Pauli exclusion principle its mass. And it's about 1.4 solar masses. It was described by Chandrasekhar already in the 30s. So we know that most neutron stars, in fact, we have observed, typically have about 1.4 plus or minus 0.3 or 0.4. Okay? Now, they already have a sufficiently large Newtonian deviation from flatness, phi, which is of order 0.1, and that is significant. We have already measured the effects of those perturbations with respect to the flatness of space in events around pulsars, where we have the measurement of light coming to us together with the deformation of space-time. We can measure very interesting relativistic effects in pulsars. Now, of course, the ultimate value that this could have, I was saying that this was a shorter radius, a factor of 2, so if phi is about 1/2, we have a black hole, the most compact amount of matter that you can construct. Actually, it's no longer matter, it's a space-time. The only thing we observe is a hole in space. We only observe the boundary of space called the horizon, and this boundary has a size which is the Schwarzschild radius for that object. We don't know that there's anything physical there. Actually, we haven't sent anyone through a black hole, which could have made observations, because it can fall down through free fall into that black hole to send back any information, because beyond that horizon, light cannot escape. And therefore, you cannot bring out information out of what's going on inside the black hole. Now, it's not the only place where phi could be a 4 to 1, also the origin of the universe, the initial stage in which everything that we observe here comes from. Again, it's one of those areas where you can measure the strength of gravity in its utmost nature, the origin of the universe and the formation of black holes. And we're going to see that those black holes, when they move, they produce objects that we can measure at large distances. And those are the gravitational waves that this talk is about. Okay, you might argue, fine, but that's something which happens in minute distortions in the solar system. But can we really observe these events happening at very strong gravity systems? Well, it doesn't have to be so to convince yourselves, because of general relativity, of course, limiting case of general relativity, which is a special relativity without gravitational fields, these two contributions, special and general relativistic contributions, modify the time that ticks in satellites moving around the Earth with respect to that ticks on a clock on the surface of the Earth. This fact means that you could, in principle, triangulate your location on the surface of the Earth by knowing the motion and distance of satellites around you. If you have sufficiently large number, at least 3 to pinpoint a point, and 4th to confirm. So with 4 satellites over the surface of the Earth, you could know your location. Except that, because of relativistic corrections, the ticking of the clock on your pocket and the ticking of the clock in the satellite is different by a factor of a few microseconds per day. Unless you correct for that, your location of the Earth would be wrong in a few seconds by kilometers. You wouldn't know where's your location on the Earth. So you have to make corrections, which are done with electronic systems, in order to correct for these special and general relativistic effects. And indeed, we use nowadays, every one of you, GPS to know your location of the Earth, thanks to general relativity. So you could tell your friends, I know that things are working, general relativity is working because I can locate myself on the surface of the Earth. All right, what else? Well, of course, if matter moves around changing space, and you can consider a distribution which is periodic in time, so it's moving and modifying space-time in a periodic way, it will create a distortion which can propagate out of that system in the form of perturbations of space-time. And those are gravitational waves. Of course, when you hear waves, I know what waves are. I've heard of waves before. There are sound waves and there are electromagnetic waves. Okay? So let's see, what are the differences between sound waves, electromagnetic, and gravitational waves? Sound waves are the most simple. They are the ones by which you can listen to me. And they are produced by distortions in the air that are transferred at some speed, the speed of sound, and they are longitudinal deformations of the locations of molecules in the air. And they are compression and rarefaction waves. Okay? So the amount of matter which is between you and me is compressed in a way which transfers energy from me to you. And this affects your ear in a way that you can recognize those distortions as sound, and you can order sound and understand speech. Okay? Now, of course, these are waves which are very different from the ones I'm going to describe. They need a medium for propagation, and they're longitudinal. They're compression rarefaction waves. But there are other waves which are very similar, those of electromagnetic waves. These are waves that exist because there are charges in the universe. And they could propagate in vacuum. They don't need a medium in order to propagate. They are those things that are located in space-time and can transfer information from one point to another, propagating at the speed that is the maximal transmitting speed in that space-time. And that's valid for any kind of perturbation of space-time. If we had some other perturber, some other field, which is not electromagnetic or gravitational, but it's some other interaction we have not yet discovered, and its propagator has zero mass, it will also move at the speed of light. It's the property of space-time which determines the speed of the propagation. Okay? It's not the property of the force itself, of the strength of the interaction. Okay? It has to do with the property of space-time that determines the speed of propagation. So they all propagate at the speed of light, at least in the context of general relativity. There are extensions of general relativity where that may change, but let's stick with general relativity for the moment. We haven't yet found any deviation in any observation that might induce us to think otherwise. Now, in the case of electromagnetic waves, as I said, you need charges. And charges move in a dipole up and down in an accelerated way, and this disturbs space-time by inducing electric and magnetic fields in this motion. These charged particles create currents, this create electric fields and magnetic fields, which propagate out of the source in straight lines in flat space. And these straight lines reach a detector. Could be the eye, could be a radio telescope, could be an ordinary telescope, it could be, I don't know, even a detector of point-like particles, like gamma rays in a satellite like Fermi. Okay? All of these would have very different frequencies, very different energies. They would all be magnetic and electric fields oscillating in time, propagating from the source to the detector. They are transverse waves. So the electric and magnetic field are transverse direction of motion. Okay? They occur on a plane. They move at the speed of light. And they have only two polarizations. It could be like this or like this. Circular one direction or circular just the opposite. All right. So what about gravitational waves? Well, these are slightly more complicated. For these, you need very large masses moving at high speeds. No wonder we didn't detect those until recently. Okay? First, the gravitational interaction is so weak that in order to produce gravitational waves, you have to have very large masses, accumulate a lot of charge, okay, of the gravitational field, that is mass. You have to accumulate a lot of charge in order to be able to generate a sufficiently large, when I mean large is sufficiently large amplitude of a gravitational wave that would propagate from one place to another at the speed of light and both transverse and moving in vacuum. Okay, they don't need any other medium to propagate. Space-time itself can be described as a medium, which is dynamical, as you know. Now, of course, how do we detect this? Well, as you can see from the flow here, gravitational waves have a very funny pattern. Rather than having electric and magnetic fields, which are transverse to the direction of motion, which are vector fields, this is a particular direction. Here, these are tensor fields. That is, when a distribution of masses on a circle has a gravitational wave that passes through, it would stretch one side while it compresses the other, the opposite. Okay? So this would open up while this one compresses, stretches, compresses, compresses, stretches, stretches, compresses. So this pattern that you can see here is not enough to put a dipole to see how it moves, because it would not change. Okay? You need a quadrupole. So what's the best way to detect gravitational waves? Well, you need two arms, which would move independently in this direction with respect to the orthogonal direction. And that's nothing but an interferometer. This was understood already at the end of the 19th century. It was some of the most interesting experiments that were done by Michelson and Morley at the beginning of the 20th century to realize that the speed of light was universal and it didn't depend on the state of motion or the orientation of the apparatus. While here, you can use this interferometer to see, as I'll show you in a minute, how the length of these two arms would change through the motion of the wave across the detector in a pattern that can result in a detection. Of course, this modification is so tiny because the interaction of gravitational waves with matter is so weak because of the weak strength of gravitational field, 40 orders of magnitude with respect to the electromagnetic one, that you need exquisite sensitivity. Detectors that can get rid of noise, the one that affects all of us and any of our experiments in our labs, to an incredible level in order to be able to detect these very tiny perturbances in space-time induced by gravitational waves. That's why it took so long. So we want to ask, if we have a particular device on Earth, what kind of systems out there can be sufficiently bright that can emit gravitational waves that we would detect here? Notice this, you might argue, well, let's construct like Hertz did in order to convince themselves that things move like in the Maxwell theory. Let's create an emitter of gravitational waves and put another detector a few hundred meters or even kilometers away and see whether we can test the existence of these gravitational waves. Problem, you need masses, which are as big as the solar mass, moving essentially at the speed of light, in order to generate sufficiently large amplitude that we would see this even, I don't know, at kiloparsec distances from us. So that's hard. We don't know. We are in a very mild part of the universe. Things that happen nearby, luckily for us, are pretty mild. There are no violent phenomena from here within our galaxy. Maybe a supernova from time to time, once every few centuries, happen. And if it's too nearby, we might even disappear as a species. It might burn us if it's too close. So most of these cataclysmic phenomena that are sufficiently bright that might produce gravitational waves are far away. And very quickly you realize, if you're familiar with distances in the universe, that distances between galaxies is much, much bigger than the size of galaxies. Distances between clusters are hundreds of megaparsecs. We need a new unit here. It's no longer parsecs, the parallax second, but megaparsecs, okay? Or hundreds, or even thousands of megaparsecs away. So they travel so long distances compared to those in the lab on Earth that their attenuation, the fact that this information has been traveled for so long, means that the intensity that we receive on Earth is extremely small. That's why we see those things extremely weak that reach Earth. We cannot have generators of gravitational waves of sufficient intensity. Eventually, I'll describe a little bit with Lisa, we might have a way to calibrate our experiment. For the moment, we just simply wait out there and wait until we receive a signal. If we're lucky, we detect it and can recognize out of noise. Otherwise, you just have to guess. All right, so what generates gravitational waves? Well, simple answer, any violent phenomena in the universe which is sufficiently fast-moving and sufficiently massive, black holes and neutron stars. The Crab Nebula is the aftermath of a fantastic supernova explosion in 1054, which passed unnoticed. That doesn't mean that people here didn't realize in Occident. But in the Arab world and the Chinese world, it was very carefully recorded. 1054, I was looking in history, what happened then? Why didn't they say something about it? Of course, this was the schisma between Occident and Orient for the aftermath of the Roman Empire. And it was a place where the Orthodox Church and the Catholic Church completely separated, much before the Protestants. And this maybe could have been that such a bright thing, which we know its distance from Earth, so we know how intense that supernova must have been. And it was clearly bright in the sky during the day. So this was so violent that it could not have passed unnoticed by Christianity. So there must have been some sociological reason why. That's why I warn you, careful with data that you might think that it's universal. No, it depends on your way of thinking, and it might affect your way of interpreting. Okay? So, the aftermath. A neutron star at the heart of the Crab Nebula, right here, which is a pulsar. It pulsates. It sends, I'll show you in a minute, it's 0531 plus 21. Those are not an age, but a location in right ascension and declination. And it's the first element of the Messier catalog of objects. Now, what is a pulsar? First, you have to ask, what's the physics of a neutron star? A neutron star is a very compact source of gravity and electromagnetic waves. Typically has a neutron core. In the outer atmosphere has a crystal of electrons, and this is rotating very fast. If it's a pulsar, several times per second. If it's a millisecond pulsar, it's about 1,000 or so times per second, so extremely fast. At the same time, because of this surface of electrons, you have currents, and these currents induce magnetic fields, and you can find tremendously large magnetic fields compared to that on Earth, which are of the order of Gauss. No? There you can find 10 to the 18 Gauss. So tremendously large magnetic fields. So what do? Well, if you have any charges around, they will be channeled through these magnetic fields, and they will be moving along the axis and thrown out in a jet of very relativistic particles, typically electrons, a few protons. And these electrons will enter into the interstellar medium. It will collide there and will emit radiation in the form of synchrotron radiation. Okay? So they are radio waves that can be detected on Earth. So we can see the pulses in radio waves coming from these objects, because if the observer is right at the end of one of these jets and the axis of rotation of the neutron star is offset with respect to this axis, you will see once, if you're lucky and the axis points towards you, towards Earth, once every rotation. Bam, 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 bam. Okay? In radio. So that is so precise that even today, deviations from a perfect timing tells you about the properties of space-time between us and the pulsars. This is pulsar timing array, a new way of detecting gravitational waves. But at the time, 1974, what they were using was this telescope, the Arecibo telescope in Costa Rica, 300-meter dish, which was extremely sensitive. It was able to measure for the first time the first pulsar, and it got the Nobel Prize for it. But not only that, it detected the deviation in time of the arrival of the pulsars. And this was crucial in order to understand that there was some energy emitted by the system that reached Earth, and that energy was carried away by gravitational waves. So, as I said, if you have a binary pulsar, so they're orbiting around the center of mass, common center of mass, these two neutron stars, and you can measure the observation from far away for this axis. From the arrival time of the pulsars, you can determine the shift in the period of those pulsars, because as that system orbits around each other and loses energy through the emission of gravitational waves, the loss of energy means that they get closer. They get more bounded. As they get closer, they emit more gravitational waves. And therefore, you can predict exactly in general relativity what is the time evolution, here as a function of year, of the time delay, pulsar rate of change of the arrival of the pulses because of the loss of energy of the system of the emission of gravitational waves. So general relativity predicted that if the system was emitting gravitational waves, it should follow the dashed line. And over decades, it was convincing enough that it was given the Nobel Prize to Hulse and Taylor. Hulse was the student that was taking data in Arecibo, Costa Rica at the time. Joe Taylor was in Princeton, and together they understood that this was a completely new kind of event. And it was a convincing motive for the acceptance of the idea of gravitational waves being emitted by a stellar system out there. So this convinced the community in the 70s that they should make an effort to create a detector, real detector, not indirect detection of gravitational waves through the loss of energy of a system, but a direct detection, okay, of gravitational waves. And NSF, for 40 years, put their efforts and energy into constructing such a detector, which eventually will produce some fruits. Now, of course, these are neutron stars. They are not the most compact objects, and therefore they're not moving at such a high speeds in the pulsar that you might say, okay, that's going to give you the largest amplitude of gravitational waves. The most natural culprits for this would be black holes. Black holes are very compact. You don't have objects more compact than black holes, okay? Anything which is more compact is a black hole. So there are certain laws in the context of general relativity and quantum field theory, which tell you that black holes are very, very special objects, okay? We can dwell into this after the talk if you want. So what instance do we know about black holes? Where did we have the first evidences that there are black holes out there in the universe? Well, probably the most famous source is Cygnus X1. We know this is a binary system. It's a star which has exploded and left behind a remnant black hole, and it has a companion which is still sending mass to this black hole through the Roche lobe, which moves gas from the outer atmosphere of this other sun or the star into a region which is called an accretion disk, which is a flattened object that can dissipate energy and become a disk. And along the motion, it creates, there is acceleration of gas, okay, which emits electromagnetic waves in many different wavelengths, okay, X-rays, etc. That's why the X here in X1, it emits an X-rays. But it also, as matter gets very near the black hole typically, because of these currents of charges, has a very intense magnetic field, which would make particles again go along the axis. So there are little jets coming out of these black holes. And this is on small scales, similar to the active galactic nuclei that we see in many, many galaxies, where you have also accretion disks and emitting jets that can reach tens of megaparsecs away. Okay? In small scale, this allows us to measure also the radio emitted by the charged particles accelerated along the axis. And we can then characterize very well what is the mass of this black hole. We can follow certain spectroscopic lines, K lines it's called from RR, and we can determine from here that this object has 15 solar masses. That's 15 times the mass of the sun, but still not that much. There are objects we can deduce their mass indirectly through the emission in wavelengths like X-rays. These are the intermediate mass black holes in galaxies like this one, NGC 2276, where we can measure the mass from this emission about 50,000 solar masses, plus or minus 10%. It's a big error. Now, there are some black holes that we can measure with much better accuracy because we can follow the motion of objects around these black holes. This is the famous Sagittarius A star. That's the star at the center of our galaxy. And this is actually not a star. It's a black hole. It's a very massive black hole. It's about 4 million solar masses. And the way we know it because we can map all of these trajectories extremely well, and we can follow the periastron, so the region of closest approach, by this one, this is S2, one of the most closest stars that are to the central black hole. And through the properties, periodic properties of these handful, about 12 or so stars, we can deduce the mass of the central black hole. And this was enough to give the Nobel Prize to Roy Penrose, Andrea Ghez, and Reinhard Genzel. It was separated into 1/3, and each one of them, one half, and they share the other half, for the discovery that black hole formation is a robust prediction of the general theory of relativity, to Royer, and for the discovery of a supermassive compact object at the center of our galaxy. These were two teams, the American and European one, which measure the mass of the black hole. Now let me go back, because I want to make emphasis that that's not the largest black hole we've known. Actually, the one that we've been able to measure with some accuracy, not because of the motion of stars, but because of the shadow of the black hole that light leaves as they move because of gravitational lensing all the way from the black hole to us, in the case of the black hole at the center of M87. That's a very massive galaxy, several hundreds of megaparsecs away from us, and it happens that the size of the shadow is very similar, that of the black hole at the center of our galaxy, than that of M87, because of a factor of 1,000 difference in distance with respect to mass, and happens to cancel out. And we have more or less exactly the same size of the shadow seen from Earth. But this is a tremendously massive object, 6.5 billion, so 10 to the 9 solar masses. And there are some, not determined with the same precision, but also quite convincingly, that can reach 10 to the 10, or even several times 10 to the 10 solar masses. Where do they come from? We don't know, honestly. We still do not know. So we want to use these black holes in order to, since they're so massive and they have companions, even stars orbiting around them, they would emit gravitational waves. Unfortunately, the periods of those stars around the black hole are so long, typically in the order of days or months, that the frequency corresponding to the gravitational waves are out of band with respect to what we have detected so far. In the future, with LISA, we might be able to detect also those black holes. So, how do you directly detect gravitational waves? First, remember this picture. Waves are transverse, they move along this axis, and they perturb the locations of particles in a circle in a way that stretches one direction and compresses in the opposite. And there are two polarizations also, plus or cross, okay? So in this direction or at 45 angles. So what do you need? You need an interferometer. So say you need one of the arms to, as the gravitational wave, and here I'm assuming the gravitational wave crosses the blackboard, it will make these particles move, and therefore as they stretch, they would move this, you see, it's moving and shifting the size. I'm assuming in the center of mass of this object, so I'm putting this at rest. And then I see that this is contracting while this one expands. This contracts and this expands, and so on. And what this means that as laser goes across this beam splitter and moves in this Fabry-Perot, which is just an amplifier of power in the laser, when it's finally reflected off, the travel time between one and the beam splitter will change along the two paths in a way that can constructively interfere or destructively interfere in the photodiode. And what you see is this, okay? You see light or you don't see. And the rhythm at which you see or not determines the amplitude and the period of the gravitational wave that passes by. Okay, so the first direct detection happened in 2015 in this tremendous achievement of humankind with these interferometers, LIGO, Hanford, and LIGO Livingston, the two twin experiments separated by 3,000 kilometers, if you want 10 microseconds, between British Columbia, almost, so in the western part of the United States, in Washington, state of Washington, or Louisiana, in the Gulf of Mexico. So, I'm going to use...
This is the sound of two black holes colliding and merging.
Can you hear?
A long time ago, in distant reaches of the universe, two black holes, each about 30 times as massive as our sun, were locked in orbit and spiraling in toward...
Oh, I'm sorry. I won't. Uh-oh.
This is the sound of two black holes colliding and merging. Where did this sound come from? A long time ago, in the distant reaches of the universe, two black holes, each about 30 times as massive as our sun, were locked in orbit and spiraling in towards each other. The only visible traces of this spinning cataclysm would have been the way their gravitational fields warped the light of distant stars. Even as they collided and merged, there wasn't a flicker of light to be seen. The real and very violent action in this system was in the form of gravitational waves, ripples in the very fabric of space and time. These waves were constantly draining energy from the black hole orbits, leading to their ultimate collision and merger to form a single black hole. At that instant, the power of the gravitational waves was 50 times greater than that of all the stars in the universe combined. That pulse of gravitational waves, lasting only a fraction of a second, expanded through the universe, passing unimpeded through countless galaxies. About 1.3 billion years later, it reached Earth. Gravitational waves alternately stretch and squeeze space itself and everything they pass through, but the effect is minuscule. Their effect on Earth here has been vastly exaggerated to help visualize something that is otherwise invisible on this scale. To detect them and directly measure their properties, scientists built LIGO, the most sensitive measuring device ever made. LIGO uses a device known as an interferometer to measure the tiny displacements in space. In this simplified representation, a laser beam is sent towards a partially reflecting mirror and split along two paths. The beams travel along 4-kilometer arms and reflect back towards the central mirror, which recombines them, directing their light to a detector. As the gravitational waves pass, the distance between the central beam splitter and the end mirror stretches along one arm and compresses along the other. This changes the time it takes the light to travel along the arms. The recombined light waves shift with respect to one another and produce a signal at the detector. Incredibly tiny stretching and squeezing of space can actually be measured directly in this way. How little does space distort to make this signal? Let's zoom into a hydrogen atom until we reach the proton at its core. LIGO is so sensitive it can measure changes in distance as tiny as 1,000th the diameter of a proton. And this tiny measurement, made by LIGO, was the final step in a journey that began 1.3 billion years ago in the distant universe when two black holes collided.
So indeed, the tremendous phenomenon of a fusion of two black holes, which emitted, as you've heard, the amount of energy per time flux on Earth at 1.6 billion years away, light years away, is 50 times the light of all the stars in the universe. Can you imagine? Of course, one is in light, and we could measure easily. The other one is in gravitational waves. It converted 3 solar masses into energy in the form of light, in this case, gravitational waves. So it's extraordinary phenomenon. We don't have these things nearby. If we would have had something similar at a few kilopascals from us, it would stretch us in a way that would make us vomit. It would modify our bodies in a way so violently that we would just feel ill. It's worse than being in the sea, you know, seasick, like I'm sure some of you may have suffered already. So it goes through 3 main stages. There is the stage of in-spiral, which could take pretty long, billions of years. Then you have a region where, and we understand this in-spiral phase very well through general relativity and its perturbations. We can treat this in the post-Newtonian approach and compute many orders of that emission with very high accuracy, and we know how it depends on the fundamental parameters of the binary, the masses, the spins, the orientation of the orbit, possible eccentricity, if the spins are precessing in the orbit, etc. All of these introduce complications in the orbit, and we can deduce this at the post-Newtonian level with in the spiral phase. Then comes a region which only recently, since 1995, we began to understand properly using numerical relativity, and that's the merger region, where the two horizons of those black holes are sufficiently near each other that there is no exact general relativity solution to it. We have to resolve it numerically. We could have to follow how the distortion of space around those two black holes is changing until they fuse, and the two horizons become one. And this object, which initially is very asymmetric, which is highly rotating, it has inherited the angular momentum of the orbit, so that this is very rapidly spinning down or emitting gravitational waves and producing a ring down phase, which is the final phase that we observe here. Okay? So the line, I don't know with this light whether you can see this, there a blue and a red pattern, which increases in amplitude and in frequency. And this is called a chirp. You heard this at the beginning. It says like, whoosh. Okay? So you increase in intensity at the same time as in frequency, and that happens because it's a runaway process, because as you move forward, you emit gravitational waves, you lose energy, and you get closer. As you get closer, you decrease the period, you increase the frequency. As you get further, you emit more gravitational waves. So this is a runaway process until the two black holes merge. And eventually it just simply rings down and no longer emits any gravitational wave. All right, so this particular pattern can be followed extremely precisely to compute the masses of objects. And this was so extraordinary that it was awarded the Nobel Prize in Physics in 2017 for their contributions to the construction of the LIGO detector and the first observation, detection, I would have said, of gravitational waves, direct detection of gravitational waves. So nowadays, it's been the 10th anniversary, a little bit more, and you might ask, what's our situation nowadays? Well, this was that event, 14th of September 2015. This is the pattern that we can ascribe to the gravitational wave, you see, with some errors, until it reaches sufficiently large amplitude compared to the error here, that you clearly see the merger and ring down, okay? So the spiral phase is not so well known. However, an object very similar, binary, very, very similar to the one that was first observed, was detected by the LIGO, Hanford, and Virgo detectors on the 14th of January 2025, 10 years after, almost 10 years after. And here's the pattern that you can see. You see the differences between these two is unappreciable. Essentially the same masses, essentially the same major axis, essentially the same distance from us, the same orientation. There are not much differences. And more or less the same area, although they don't overlap. The same area in the sky at the same distance. So we have more or less the same sensitivity in the different detectors, and therefore we can compare our ability to detect these objects by comparing the noise, the purple lines here. These purple jagged lines are much wider in amplitude here in September 2015 than here in January 2025. That's the improvement in the sensitivity of the detector. That's how the first event, same distance, same masses, had a 25 signal-to-noise ratio event, while the one in the lower part had an 80 signal-to-noise ratio event. So it's like a 12 sigma compared to a 5 sigma, okay? So it's a tremendously loud event, very well characterized. So well characterized that we can ask fundamental physics questions. And I won't dwell into that, perhaps afterwards in the session of questions, because understanding the merger and ring down phase, we can start to test the properties of general relativity in the strong field regime. We can ask things as basic as, does the area law of black hole horizons is satisfied in this event? And indeed it is. So we can begin to test modifications of gravity to the level of a few percent, something which in the strong field regime had never been achieved. It's a completely new arena for exploration of gravity and its extensions. So these events initiate a new era. It will open up more exploration of the universe. Here you can see the effect in the chirp. This is, you see the difference? I'll show it again. 2015, you see? 2025. See how bright it is? Okay, on the same plot. So not only that, you can see how, by making simulations, we can ask ourselves, Can we trace back the motion of these two black holes so that we see what happens when they merge? And how many different components of space-time is involved? What, in the jargon of gravitational physics, are called the ring-down quasi-normal modes. Can we determine what are the different components of the emission of gravitational waves? And here you see a breakup. Your first tone in the ring down, it's similar to what happens when you beat a drum. You're hitting it, and then you let it perturb down. So you see there are several tones. In the last of these events, we've seen the first, the second, and the third tone as they die out. And we can follow in time the dying out of the tones because the rate at which they die out gives you information about the mass and the spin of the final black hole. And since there are only two parameters that characterize the space-time of a Kerr black hole, we can see whether the three tones satisfy a constraint equation and gives you exactly the same mass and the same spin. And indeed they do. So we are testing modifications of general relativity which predict different relations between the different tones. Now, of course, this is just one of those events that have been measured. Already published, there are 300 compact binary coalescences, a few neutron star black holes, a few black hole binaries, only one directly detected in electromagnetic waves, but there are about 300 or so already measured. There are, let me turn this off because I'm not going to use it again. Well, I'll give it back to you. But there are about 100 which are not yet published. Soon there will be a GWTC5 catalog, which will contain many more events, and they're going to appear in a few weeks, okay, for more corroboration. And this is how they distribute. In run 1 and 2, there were just a few. Soon in run 3, when we added also Virgo, we had the possibility to detect many more at much higher distances, look back time or distance. And in run 4, we saw hundreds of those. This was much longer, about 2 years. So we have many which have not yet been published. There were only alerts. Alerts reach everybody in the astrophysical community. They could follow up the location, the intensity, and the false alarm rate of those objects. You can deduce whether they are candidates for your particular physics, and you can explore them. And there are many satellites and telescopes on Earth that have followed some of these alerts. Now, where do they distribute? Of course, this is a pattern that the collaboration decided to show. It looks like an eagle, but there is no reason to put them in this order. The only thing you see is that every two of these pairs become a final one. You see that they sum up essentially to that mass. So some of them have the neutron star as companion, and then they form a binary and a merger into a black hole. And some of them have certain uncertainties. We don't know whether they are neutron stars or black holes. Those that are here in red and blue simultaneously, unfortunately, the lights are not good. And I cannot, maybe you see this from the back. These are neutron stars. Sorry, black holes that have been observed through X-rays, not neutron star. Neutron star are this, the yellow ones, below about 2 solar masses. But there are regions which should not be populated, and still they are. There are 3 basic areas. The peri-instability supernova mass gap has to do with the physics of supernovas. I won't go into the details because it's per-producing electrons and positons which take away some radiation pressure, and this produces the star to collapse without leaving any remnant, and there shouldn't be any black hole in this gap. And we've seen many, hundreds of them, in fact, already, several tens. I'm exaggerating with the hundreds. Now, there is another region between 2 and 5 solar masses, again, where we have no evidence whatsoever that a supernova explosion might have left these objects. We have seen some supernova explosions that we could follow in what's inside, and most of what we've seen, at least in the Milky Way galaxy, are neutron stars. They're not black holes. Okay? And then there is a very clear limit that I was describing based on fundamental physics, the Chandrasekhar limit, having to do with the Pauli exclusion principle of neutrons, that you cannot compress further. There's a pressure, degeneracy pressure, which prevents collapse unless the mass is above 1.4 solar masses. So if we see any black holes below, significantly below 1 solar mass, definitely they must have some other origin. They could not have been formed from the collapse of ordinary matter. They must have had a collapse from, I don't know, photons, which are bosons and can compress. There's nothing to prevent collapse of photons. All right, so this is the distribution nowadays in GWTC4 last year. So they're not uniformly distributed. It's something which I was discussing with Tom. There are some below 2 solar masses, very clearly indicated. There's no doubt that there are some of which, for instance, like this one, has a very large mass ratio, 32 solar masses against 1.4. We don't know what this object is. It's very far from the diagonal equal masses. Most of the black holes lie in this region of about 50, 10 or so, and there's a peak here, which for the moment, GWTC4 we don't see. GWTC5, which will appear soon, you will very clearly see very dominant. So there are like 3 peaks. Why are there 3 peaks? Why do they happen to lie in those ranges? Why aren't they uniformly distributed? We don't know. So we're opening up new avenues of research. We're trying to ask at the statistical level, where do these black holes come from? Certainly, when the first black hole, which is one of these, appeared, everybody was puzzled in the astrophysics community. Where did this 40 solar mass black hole come from? We don't have stellar evolution systems that produce such big black holes ordinarily. You need very special situations for those black holes to form. Nowadays, we know that there's the majority of the gravitational wave systems have masses around this. So how are they formed? Are we opening up new channels in astrophysics, or do they have completely different origin? And we're still debating, okay? Now this, of course, has opened the title of the talk, the Gravitational-Wave Astronomy. We have several detectors, some of which have been already started digging. I was there. It's few slides only. But there are some in Cagra, LIGO, and Virgo, which are already operating with more or less success, and GEO-600, which has stopped operating, no longer in function. But it has been in the past because we were hoping that we might see a supernova explosion nearby in our galaxy so that even that would be detected by GEO-600. It would have sufficient sensitivity to help triangulate the location of the source. All right, so these detectors have allowed to locate in the sky objects. Of course, you might say, come on, with a region as big as this from the first event, you cannot locate any object in the sky. You only know more or less the area where the object happened, okay? If you find another object which happens within this area, well, that's easy, because it's so big that it could consider whatever other event would happen there. So we cannot do astronomy yet with gravitational waves, except if we have a multitude of detectors, and we are going in this direction. We will have eventually 5, 10, or even more detectors on Earth. Some are already starting in, as I said, in LIGO, India, but also in Australia. And eventually, we might reach areas which are of the order, like this one, 1708-17. This is the famous binary neutron star in this direction, which occupy an area of about 20 or so square degrees, enough to locate the source, which was a galaxy, NGC 4993. So some of these might be traced back to objects if we have also electromagnetic counterparts. But most of these only emit in gravitational waves, and we cannot tell where the source is. Imagine an object like this one, okay? Eventually, we will be able to locate within a few square degrees, nowhere near the few arc minutes that you do with ordinary light telescopes, or the micro arc seconds that you do with radio. Okay? So we're still not in the situation in which we can compare the electromagnetic resolution from visible to gamma rays, infrared, soft X-rays, hydrogen, dust, and microwaves. Okay? Each one of these gives you a completely different picture of the universe, radically different, because they tap different sources. The envelopes of stars, the dust which is between stars, the emission of the cosmic background in microwaves, etc. All of these tap very different sources. Same will happen with gravitational waves. Even though we've only opened a little window in the 100 hertz band, eventually there will be other bands. There will be bands that will allow us to follow continuous sources, spinning neutron stars. So these are stars that have a little mountain and they orbit very fast. So they're creating gravitational waves with a given amplitude. If they're sufficiently close by, we might be able to measure this. You need a big mountain in a big neutron star in order to see that. And we haven't seen, we've put bounds on this. We could follow some of the pulsars, so we know they don't glitch that strongly, if you want. Now, of course, we have seen some of these, black holes and neutron stars. We haven't seen yet these bursts, in general, unmodeled transients, not only supernovae. We hope that we might see a supernova in one of our nearest galaxies. Then they would be sufficiently bright that would be able to correlate both light and gravitational waves. And eventually, we might see the stochastic sources, gravitational wave backgrounds, from the Big Bang, or from other sources. For instance, new exotic physics like cosmic strings that Jose Juan here explores, okay? Physics which go beyond the standard model of physics that we know so far, and could leave sources in the form of gravitational waves. So it has opened a window into exploration of things which we would not have had the opportunity to measure. Now, in multi-messenger astronomy, you have the possibility, if the number of objects increases sufficiently, to follow simultaneously the emission in light and gravitational waves. And even if it's sufficiently close, not only this, but also neutrinos from the decay, particle physics decays of pions, as well as so protons into pions, pions into muons, muons into electrons, and eventually all of this cascade can reach Earth simultaneously with gravitational waves and light. If this is sufficiently close, even protons might reach us. So you would have 4 components. You have light, as usual, gravitational waves, the new window, neutrinos with high-energy detectors, like the ones in South Pole, and protons, cosmic rays. So these 4 different messengers contain very different information about the physics of the object that created the event, and we can then observe at different depths within that cataclysmic phenomenon. It could be an active galactic nuclei that emits in all of those different messengers and detect them, all of them, simultaneously to open up our eyes. And this is the kind of phenomenon that we might see. Radio, optical, gamma rays, neutrinos, the new components, and gravitational waves in the future. This is what LISA will see towards the galactic center. This is already, this is an expectation, okay? Of all those images, it's the only one which is not, we've not yet have. The rest we do. Neutrinos with the ice cube in the South Pole, gamma rays with Fermi, optical for many decades, and in radio since the 30s of last century. So you see each one of them has a completely different view of the central part of the universe. Sorry, the central part of the galaxy. So in the future, we've reached second generation detectors up to redshift 2 or so. This was one of the most extraordinary events, and we should put here the 250114. But eventually we would reach, say, distance of over 100 in redshift with the Einstein telescope, and with the next generation, in this case, in space, satellites in space, LISA, we might reach even distances of over the microwave background. So we would go back in time tremendously large distances. Einstein telescope is 100 meters below the ground to get rid of the seismic noise, and you have this kind of sensitivities to masses and redshift. You see, you could cover all the way with LISA all the way to 1,000, essentially to where the microwave background is. Now, by finding objects as heavy as, say, 100 or 10 or 100 solar masses, at redshifts above 100, we will begin to question the stellar origin of these objects. How could you have formed black holes so massive so far, so early in the universe? Okay? We still have not reached such a stage. Eventually, we might. So, the real revolution would come with LISA. I think this is loud enough. I don't need the microphone. This is an idea put forward initially by ESA and followed up by NASA to send a satellite made out of 3 individual satellites that would be launched from Cape Canaveral. We don't know yet who's going to launch it. It might be even SpaceX if it has Falcon 9. Well, don't worry about the noise. This is just propaganda. So you see that it generates 3 detectors which separate in space and form a triangle with a distance of arms rather than few kilometers like LIGO Virgo would be 2.5 million kilometers. Okay? 150 million kilometers is what separates us from the sun. So 2.5 million kilometers is a significant fraction of the astronomical unit. So these are satellites that will be able to receive the light from the other satellite. In this case, it's a laser, which travels 2.5 million kilometers. You first have to orient and know where they are in space very well. And then see, as they move in geodesics around the sun, they're orbiting just like the Earth, slightly ahead of it. It's just orbiting at 60 degrees from the Earth, always in orbits, periodic orbits, of a year. At that distance, all objects in a geodesic follow the same orbit. But they're orbiting, moving around that trajectory, always at the same distance, as you'll see in one. So here what they're doing is pinpointing in space the location of stars in order to navigate, to know where they are. Then they emit a laser beam towards one of their satellite companions. You see, this was the source, and this detector will then rotate, receive the light, and say, I got it. I know where you are. And then it would send back a laser. And it will measure the time of arrival and the time of that it has traveled from one object to the other. It's delayed time interferometry. It's not the usual microsound interferometry. There's not enough power in the laser to go back and forth, like in LIGO, okay? So you're measuring only the time delay of arrival of the laser. And here you have the three in a triangle. You see how it's traveling? And by this motion, you can then look at a source which has not yet merged and follow the in-spiral phase with very high accuracy. As this moves around 1 year after, you may be able to pinpoint the location of the object to within 1 square degree. You can triangulate for a year. It's like using parallax, okay? But not with light, but with gravitational waves. So you would be able to know where the location of the source is, and from here, interpret this in terms of whatever there is. Okay, so that's the final slide. You see how they orbit around. Actually, this was the Earth before. It's actually, this one is going. It's a wrong rendition of the experiment. You see how they travel, moving in space? So the plane is not always orienting in the same direction. That is necessary in order to really pinpoint well and cover the full sky. Okay. So the wave spectrum that we've explored nowadays is only the terrestrial interferometers, and we can go to longer and longer wavelengths towards the microwave. But there is a very important effort done to explore beyond this to high-frequency gravitational waves, something which we are involved in, because it would open to phenomena that are not produced by ordinary astrophysics. And with this, I finish. Thank you for your attention. And sorry for being over time. It took my time to get on with it.
Thank you very much for a very nice talk.
It's not working.
Is it working? So
yeah.
I think we have time for a quick question. Maybe more than one. Yes.
I must say that if you're interested in other aspects, what are these objects really coming from? So I will have a more, say, directed talk after lunch for those that want to follow.
So, yeah, here.
Yes.
So, yeah, I wanted to ask you about memory effects. So, gravitational memory effects, as you might know.
I guess many of these people don't know what a memory
I know.
effect
So
is.
this is the permanent displacement, right, between two free-falling masses after the passing of a gravitational wave. So this is the most basic memory effect.
Mm-hmm.
So I was wondering if the new generation of detectors would explore these effects.
Yep,
So
this is one of the objectives of LISA and ET. At the moment, you've seen that the noise is pretty high. It's very difficult to see right after ring down whether most of those fluctuations which we see in noise actually are displaced with respect to what happened just before the merger. So it's very difficult to see these memory effects at the present stage. For this, we would need probably signal-to-noise ratio of 1,000. This means very massive objects not that far away. Okay, so supermassive black hole binaries, two black holes of 10 to the 6 solar masses orbiting each other, would leave a second-order memory effect after the ring down, which could be measurable. There's one other way which is much more ingenious, and that's called the first-order memory effect. And that happens when, not when there is a merger, but when there is a close hyperbolic encounter. This happens when you have two objects that rather than being bounded, and therefore orbiting in elliptic orbits, they're actually hyperbolic orbits. So what happens is that they get close together, they bremsstrahlung, in this case not light, like gravitational waves, as they pass closer, and then they move out. So you see a burst, okay? In the amplitude of gravitational waves, you see a burst. In that case, there's a specific, this is a linear order, which is much more important than the second order gravitational wave that you were describing, memory effect. So this first order might be seen, right? Possibly, if we have an event, a close hyperbolic event, sufficiently near us. But for this, again, you need large masses and high velocities, okay? This has been explored, among us, by my group, and there is a chance that if things go as expected in 05, the fifth run of LBK, we might be able to see it there. It would be tremendous, because it's one of the most concise and let's say, robust predictions of general relativity. We should see that kind of effect happening in gravitational wave orbits. You're welcome.
Any other question?
I see a question here. A hand up, at least.
Thank you for your talk.
You're welcome. My pleasure.
At the beginning of the speak, you said that a black hole was no longer a matter, but space-time. So that got me thinking, are there, what new ideas are today for understanding this Paris instability mass gap for these black holes of 40 solar masses of the Paris instability mass gap? Are there new ideas of understanding what a black hole really is, or are?
It doesn't help you because there are astrophysical phenomena that might fill that gap. If you have a previous merger which has increased the mass of the black hole above the gap, then they will not produce from a supernova explosion, and therefore they're not bound to this or to this gap constraint of the Paris stability. So you might argue if we observe them there, we should see black holes of above 40 or 50 solar masses. However, there's always a however. However, if these objects come from a previous merger, remember one of the most important aspects of black hole mergers is that they inherit the orbital momentum of the binary. And this makes a very strong prediction for what kind of a spin should the remaining black hole have out of this previous merger. It's not just an increase in mass. Even if they had no initial spin, they would end up with spin, because they inherit, as I said, the orbital momentum of the binary. So this means that the spin to mass ratio should be of order 0.7 or so, typically around 0.7. We have not measured any, well, sorry, there's only one out of 100 events that are above the Paris stability mass gap in that band, which have a spin of 0.7. All of them have a bit 0.3, 0.1, even 0. No spin at all. Now, those objects could not come from previous merger. I'm sorry. There's no way we can shed away angular momentum of a black hole. We can only increase it, okay? So somehow, there is, in the community, tremendous unrest because we don't understand how those black holes could reach such a high mass without also increasing their spin. There is, however, an alternative, which has been put forward many years even before the first detection of gravitational waves, and that is that our universe is filled up with primordial black holes. They were not produced out of stellar evolution. They're produced from the collapse of matter, in this case, a gas of photons, in the early universe, at the time of QCD, where you had only quarks, gluons, photons, and electrons to form the matter that collapsed to form a black hole. And since you pointed out from my initial part of the talk that the only thing we measure of a black hole is the properties of the surface, of this boundary of space, we don't know what a black hole is made of. If a black hole would have baryonic number, if we would know whether it was made of baryons, photons, or some other quantity, we might be able to tell apart primordial from stellar black holes. Since the only thing which remains is mass and spin, if it had charged, you might have some possibility. The mass, all the black holes that we've measured in the universe today have no charge. The universe is neutral on those scales, okay? And if they had, it would have been shed away very quickly by emission from Hawking radiation. So all of those black holes only have two numbers, mass and angular momentum. So if none of those two numbers fit in that band, maybe we have to convince ourselves that these come from a different origin. Of course, like many people have said, in order to make fantastic claims, you better have fantastic evidence. Means that the community is not going to accept primordial black holes straight away. They're going to be extremely critical, and I think we should all be very critical. And it's one of the reasons why I became part of these collaborations. I was called out, please help us see whether some of the events that we are measuring might or might not be primordial black holes. Maybe you have a way to tell apart. Even though I'm a theorist, I was asked to be part of those collaborations in order to help with interpretation of some of the events. For the moment, I must say, honestly, we have not seen any event that is clear-cut a primordial black hole. We haven't seen any of those subsolar mass that are so clearly a 5 sigma event or a 25 signal to noise ratio event that we might convince the community that they are primordial. There are some candidates, but okay, I have become very, very cautious with my statements, never to say something which I want to retract afterwards. We've had this experience for BICEP 2, so we better be very, very careful not to claim before we understand our errors.
Just on that point,
yes.
There's continuity in terms of the correlation between the component masses.
Yeah.
I mean, I think that's pretty striking that
it is.
They're so similar, and that remains true above this mass gap as well.
That's
so,
right. It also bothers me.
So what you would like is an explanation for the whole population,
yep,
rather than...
I agree. It's a very good point. Okay, for the moment, the detectors are noise-dominated, okay? We still do not have a signal-dominated detector of gravitational waves. We have to wait for LISA for this. That means that for the moment, since we cannot calibrate well, what we measure, we have to try to understand individual events as part of a population, like you're saying. So we need to do statistics with this. When you have a small number of statistics, you can do very little. If you want to be very careful about this continuity in the mass distribution, whether indeed there is a gap after 50 solar masses that might suggest that indeed there is such an astrophysical origin of those black holes or not, it's statistical at the end, okay? So we have to be careful in the sense that there are this, of course, inherent in doubt that we have of the statistical populations of those black holes, not to make bold claims that there is indeed a new population of primordial black holes filling up the gap. But it is surprising, and it bothers me to see that there is no discontinuity. The mass keeps on, you've seen the image, keeps on going beyond the 50 solar mass without any problem all the way to 130 solar masses. Why? If there was so scarcity of black holes in that area, at least we would have seen the stellar population cut, and we don't see it, okay? So, but that doesn't prove the opposite. That doesn't prove that they're not stellar. It only means that I still don't have a good argument for these being not stellar. So you have to be very careful with your reasoning. In the future, I was saying about the signal dominated. With LISA, there are certain binaries. Remember the pulsar which was emitting gravitational waves? Again, they were at a few light-second distance from each other, okay, and therefore the frequencies were comparable to those that LISA will be sensitive to, okay, 100 seconds. So in the millihertz region, okay? So that means that in this region, we will see some binaries that we've already detected in light. We see that there are these stars which are emitting, which can be used as a lighthouse that we know must emit gravitational waves. So they are called the confirmation binaries, because we know that we know the distance very well with Gaia, and therefore we know that they should emit at this amplitude. So we should detect exactly the amount of gravitational waves that those objects are actually emitting. And this will be for the first time. It will not be man-made, but it would be an experiment like that of Hertz. We have an object which we know emits gravitational waves, and we have a detector which can measure those gravitational waves emitted by that system. And this will allow us to calibrate the system. And then we will ask these kind of questions about populations. We'll have hundreds of thousands, not just a few hundreds. That's the future. Many of you probably will end up working in this area. It's eating up particle physics experimental directions nowadays.
So since we run a little bit later than usual.
There was another question.
Were there more questions?
Okay, never mind. You can come afterwards.
The
I'm still going to be
good
here.
news is that Juan has agreed to keep talking. We're going for lunch, but then after lunch we're going to meet in the theory department. And
Once I start, it's difficult to shut me
so
up.
if you want to, if you want to chat
That's
to
what he
him a
said.
little bit more, you can come to the department afterwards and ask him questions. Okay? All right. Let's thank him once more.
Muy bien.